What is a radian? One of the toughest questions for some kids to understand in trigonometry. So let's talk about the definition of what a radian is. So this is a definition you might find in some textbooks. The radian measure of an angle in standard position is the ratio of the length of the arc of a circle centered at the origin, subtended by the angle to the radius of that same circle. What? Yeah, very confusing definition with lots of big words that maybe we don't understand yet. So let's try to really break this down so you can easily understand what a radian measurement is. So the first part about this, it says the radian measure of an angle is in standard position. Okay, so to measure an angle in radians, we first absolutely positively must be in what we call standard position. So let's talk about what standard position is. In the coordinate plane, an angle is in standard position when the vertex coincides with the origin and one ray coincides with the positive x-axis. The other ray is called the terminal ray. Positive and negative angle measures indicate rotations from the positive x-axis in the counter and clockwise directions, respectively. Angles in standard position that share a terminal ray differ by an integer number of revolutions. Mind blown. What? This is way too wordy. So let's unpack all of this, right? I want you to leave this video understanding what a radian is. And a radian is how you measure an angle if it's in standard position. Here's the definition of standard position. All right, let's break it down. So first off, we got a coordinate plane. Everybody knows what a coordinate plane is. That's our standard x, y axis, our land of x's and y's. That's the coordinate plane, right? And the first rule is that the origin must coincide with the vertex, or the vertex must coincide with the origin. So there's my vertex right there of my angle. The first initial side, we would call it, the initial side, the starting point of your angle must be on the positive x-axis. It's got to be on this positive x-axis. Then we start to, rotate our angle. And we could rotate up like this. That's going to be a positive angle, which would go in the counterclockwise direction. Or we could, if we wanted to, rotate our angle in a clockwise direction down and go all the way around. That would be a negative angle. So negative angles simply start on that positive x-axis and go in a clockwise direction, where positive angles start on that x-axis and go in a counterclockwise direction. So that is what an angle in standard position looks like. Now, let's talk about this angle. I'm going to call this angle theta, just to kind of honor the Greeks, right? We typically, or you could call the angle anything you want, but we just usually use Greek letters, and very famous Greek letters, this like slanted O with the line across through it. That is theta. It's just a very common Greek letter that we use for angles. All right, so if I want to measure that angle, one thing that you may say is, let me pull out my protractor. Well, protractors, that's a measuring tool. Throw that away. We don't want a protractor. And who even made up what a degree is, right? Like, it doesn't even make sense what 1 degree is 1 degree. Like, why are there 360 degrees in a circle? Why not 4? 4 might actually make more sense, because if you think about a circle, you can easily break it down into 4 sections and 1 degree each. Regardless, degrees are stupid. Sorry if that offends you. So we want to find a better way to measure this angle, and that's what some of the Greeks did. They said, all right, let's break it down. Let's actually look at this angle. So first off, if we were to swing this angle all the way around, obviously it would make a circle, right? If we would go all the way around, we'd get a circle. Okay, cool, awesome, fantastic. So the section of the circle that our angle creates is called a subtended arc. Okay, kind of a weird word, but think of it as the subset of the greater circle, right? It's a section of the circle. So, and that length of that arc, the length of that arc is created by the size of the angle. A smaller angle is going to create a smaller arc. A bigger angle is going to create a bigger arc. So let's call the length of that arc S. Now I'm going to use S because it's a section of the circle, or the bigger word is it's the subtended arc. It's the subset of the greater circle is that length of the arc. So what the Greeks set out to do was they wanted to measure this angle right here. not in terms of a protractor with some measuring device. They wanted to measure it in a way that actually makes a lot of sense. So what they did was they looked at the radius of the greater circle, which would be, this right here would be the radius, and so would this, right? The radius is the distance from the center to the edge of the circle. And they wanted to look at the relationship between the length of the arc an angle creates and the radius of that circle. And that relationship is how we came up with radians. So let me explain this a little bit more here, right? Imagine if we were to make a much bigger circle, and a much bigger circle would have a much bigger radius. And if we were to swing that radius around to make it circle, I'm actually going off screen here, sorry. But the point is we would have a much bigger arc. Much bigger radius, much bigger arcs. That is such a terrible drawing because I'm going off screen. But my point is, it's a bigger radius, produces a bigger arc. But what did not change? The angle, right? The angle's not different. The angle's the same. It's just bigger radius made a bigger arc, but the angle is still the same. I can even make a shorter radius. Maybe here's a blue radius that's much shorter than the red or the green. And when I swing that radius to make an arc, I have a shorter arc. So I have 3 arc lengths here. I got the blue kind of small, I got the green kind of medium, and the red kind of large. They're all different arc lengths, but they also have different radiuses. But the one thing that's the same is that angle. So what the Greeks said is, hey, why don't we do this? Why don't we measure that angle? Not by pulling out some crazy protractor that who knows if they were even invented back then. But let's say that we simply look at the ratio between the length of the arc created by a circle's radius. And that is the formula for measuring angles in radians. You simply take the length of the arc created, the subtended arc, and divide that by the radius. So when we go back up here to the definition, here we go, right? The radian measure of an angle in standard position is the ratio is a fancy word for saying a division problem, a numerator denominator, of the length of the arc of a circle centered at the origin, subtended by the angle, so the length of the arc created by the angle, to the radius of that same circle. And that's how we came up with this idea that an angle in radians is the ratio of the arc length, the subtended arc of the created by the angle, divided by the radius. There's our formula. And the cool thing is, if I use the red arc length and the red radius, that ratio is the same as the green arc length and the green radius, and that arc length is the same as the blue arc length and the blue radius. It's all going to get me the same measurement for that angle. All right, so here is that official definition for what a radian is. A radian measurement is the arc length divided by the radius. Nice and simple. So let me just draw you another example here. So if here's my radius right here, r, and I swing an angle way over to here, that's going to be a pretty big size angle, right? And I say, all right, I want to measure that angle. Well, I'm just going to take the length of the subtended arc, the length of the arc created, and I'm going to divide it by the radius. And that ratio between the arc created and the radius is going to get me my radian measurement. Now, the cool thing is there's no units on radians. Think about this for a second. If the arc length is measured in inches and the radius is measured in inches, when you divide them, those inches are going to cancel out. They're gone. You just have a single value that represents the radian. This is even more important because this actually means that radians don't even care what your units are. The units will actually cancel out and go away. They don't even matter to the problem. I could measure this length in Skittles. Like, think if I laid out a bunch of Skittles and I was going to say, oh, that arc length is 57 Skittles long and that radius is, 23 Skittles. Well, you just take the arc length in 57 Skittles divided by the radius, 23 Skittles. And the measurement of Skittles doesn't even matter. It's a crazy measurement, but it cancels out. It's gone. And you just get a radian measurement of 57 over 23. Grab a calculator if you need to. 57 divided by 23 would be an angle of 2.47 radians. Okay? And another way of thinking about this, if you're still looking for ways to really kind of concretely make sure you understand what a radian is a radian is basically measuring an angle in its radiuses. So if I were to think about taking the length of the radius, Okay, so let's just say that I got a piece of string and I measured the length of the radius and I called that piece of string R because that piece of string was 1 radius long. And if I were to take that radius and I were to lay it out across the circle, when that string ends, I have 1 radius. So when my arc length is equal to my radius, when the arc length S and the radius R are equal, whether it be 5 and 5, 10 and 10, 13 skittles and 13 skittles, 50 feet and 50 feet, or 10 inches and 10 inches, I'm going to get 1. So 1 radian occurs when the arc length is equal to the radius. And then if I take 2 radiuses, so I'm going to lay that piece of string out again. That piece of string was a radius long. And there I have 2 radians because my arc length is double my radius. So I would have, again, regardless of what that is, 20 divided by 10, 50 divided by 25, 100 divided by 50. If my arc length is double my radius, I got 2 radians. So hopefully that makes a lot of sense, and that's pretty simple. All right, one last thing I want to do to really kind of hit home and talk about radians here is how many radians are in a full circle. So let's actually look at a full circle here. So if I have an angle, again, standard position, vertex at 0, 0, the initial side where I start is always that positive x-axis, which is going to be my radius. And if I were to go all the way around and my terminal side would land right on my initial side, I would have a full circle, 1 full circle. So what is the radian measurement for 1 full circle? Well, the radian measurement formula is the arc length divided by the radius. So what is the arc length of 1 full circle? Well, the arc length of 1 full circle is, we actually have a name for that. It's called the circumference. The circumference is the entire distance all the way around a circle. So it'd be the entire circle. And the circumference of a circle is 2 pi r. So the arc length of an entire 1 full circle is the circle's circumference, 2 pi r, and then the formula for radian says to divide by r. So those r's are going to cancel. They're going to reduce away to a 1. Again, whether they're in inches or feet, it doesn't even matter. Those are going to reduce. And all I know is that in 1 full circle, I have 2 pi radians. Now, if you're looking for an approximation on that, 2 pi is approximately 6.28. No units there, it's just radians. So if I were to measure the length of this radius with a piece of string, and I were to lay it out, and wherever it stops, there's 1 radian, laid out again, there's 2 radians, laid out again, there's 3 radians, laid out again, there's 4 radians, laid out again, there's 5 radians, laid out again, there's 6 radians, and I don't have enough room for a full radian, which is why there's a little bit extra, so hence 6.28, or exactly 2 pi radians in a full circle. And guess what? If I make the radius smaller, terrible circle, sorry. But if I make the radius smaller, my arc lengths become smaller. But I still have 2 pi radians in that circle. Just because it's a bigger or smaller circle is not going to change the amount of radians that I have in it. Just like no matter the size of a circle, you got 360 degrees. No matter the size of a circle, go around it once, you got 1 revolution. So if I go around a full circle, I got 2 pi, 6.28 radians, regardless of what the radius is, because that unit's going to cancel out anyway. So I hope this video really helped you understand what a radian measurement is. It all starts with an angle in standard position, and then it's literally just looking at the ratio, the division of the length of the arc created by that angle inside of that circle. So it's the subtended, the subsection of the greater circle. That's just your arc length divided by the radius. Boom, that's it. And when your radius and your arc length are the exact same, then you have 1 full radian. So radian measurement is basically measuring the size of an angle based on how big its radius is. Makes a lot of sense. All right, hopefully you enjoyed it. Hopefully that was a nice, easy way to understand radians.